Having spent considerable time on probability theory, now we'll shift our focus towards statistics and statistical methods. Now, while probability calculus, starting from distributions, predicts properties of random samples, in statistics, given a data sample, we look for a theoretical description of the population from which it has been derived by some random process. In the simplest case, the sample consists of independent observations randomly drawn from a parent population. Usually, we either want to check whether our sample is compatible with a specific theory, or we decide between several theories, or we infer unknown parameters of a given theory. So, if we have to give a summary of the different kind of cases we can encounter, then we can in each case we can discuss what the given information is and what we want to do with it. So the first case would be that we have a number of alternate hypotheses. So let's say we denote by hi, and what we want is to figure out the relative probabilities for the validity of these hypotheses. A second case could be that we have a single hypothesis and what we want is to get a quantitative statement about the validity of this hypothesis. A third option could be that we have a valid hypothesis which is characterized by either a single parameter or a set of unknown continuous parameters and what we want is a best value of this parameter or this set of parameters and the uncertainty associated with that value. So this third case basically corresponds to what is known as parameter inference. Now, in this lecture, this is what we are going to look into in considerable detail. So let's start with So let's say we want to do inference with given prior. This will basically bring Bayes' theorem into the picture. And let's first concern ourselves with discrete hypotheses. Now we know that conditional probabilities allow us to write relations like these. Probability of A intersection B is nothing but the probability of A given B times probability of B, or probability of B given A times the probability of A. So we'll apply this relation to a discrete random variable K, and these hypotheses Hi. This index I, which is denoting the hypothesis, is to be interpreted as a random variable itself. So we'll assume that the probability to observe K is given for a finite number of alternatively exclusive hypotheses. So what we can write, P of K given Hi times probability of Hi is nothing but the probability of Hi given K times the probability of K. We have basically replaced A and B by K and Hi. And this allows us to write the probability of Hi given K is the probability of K given Hi times probability of Hi divided by probability of K. The probability of Hi is the assumed probability for the validity of the hypothesis I before the observation happens. So it is the a priori probability, or in short, we call this the prior. Now the computation of P of K, which is the marginal distribution of K, that is the probability of a certain observation summed over all hypotheses, yields Pk equals sum over Ai, P of K given Hi times P of Hi. So which allows us to write P of Hi given K as P of K given Hi times P of Hi divided by the sum over all i's. Let's call it J to avoid confusion. So the probability of the validity of the hypothesis Hi after the measurement K is basically equal to the prior times the probability to observe K if Hi applies divided by a normalization factor. When we are only interested in the relative probabilities of two different hypotheses for an observation K, the denominator basically cancels. So for relative probabilities, what we are interested in is P of hi given k divided by P of hj given k, and this is simply this ratio. Now what we have outlined for discrete hypothesis, the same can be done for a continuous case. So the case where the hypothesis index is replaced by continuous parameter theta. That is, we have an infinite number of hypotheses. And then Bayes' theorem becomes so instead of the intersection, we have the joint probability. It is given by the product of the conditional probability of x given theta times the marginal probability for theta, which also equals the conditional probability of theta given x times the marginal probability of x. So for an observation x, so basically the conditional probability of theta given x is and again the marginal probability can be computed by integration over all theta. So from the probability density of this parameter that we are interested in, we can derive the best estimate and an error interval. One obvious choice for the best estimate is the expectation value, and for the error interval is the standard deviation. So therefore the estimate which will denote as theta hat is a function of the observations. At this stage, we must remark that a function of the observations is called a statistic, which must be distinguished from the mathematical discipline of statistics. Now, usually, we do not know the prior, or our ideas about the prior are rather vague. So in the absence of prior information, the only element that we have to judge the relative virtues of alternative hypothesis is the likelihood ratio. So let us give a definition. The likelihood which will denote by Li, of a hypothesis Hi, to which corresponds a probability density Fix is f of x given Hi, or for the discrete case, let's call it Wi of k, p of k given Hi, when the observation so likelihood is basically equal to Li, the likelihood of I given x, is given as Fi of x, or for the discrete case, Li of k is Wi of k. Now the index I, which denotes the hypothesis, is treated as an independent random variable. When we replace it by a continuous parameter and consider a parameter-dependent PDF or discrete probability function, then the corresponding likelihoods basically I have L theta, which is L theta given x equals fx of theta, L theta given k is W of k theta. If the likelihood depends on one or several continuous parameters, we talk of a likelihood function. It must be remarked that the likelihood function is not a probability density of the parameter. It has no differential element like d theta involved and does not obey the laws of probability. Usually, experiments provide a sample of n independent observations xi, which all follow independently the same PDF, which depends on the unknown parameter. In these xis are also known as IID variates, or in other words, independent and identically distributed variates. In such a case, the combined PDF is simply equal to the product of the n simple PDFs. So what we have is f tilde for x1, x2, all the way up to xn given theta. This is a product that goes where I goes from 1 to capital N. And similarly for discrete variates, we have w tilde for k1 up to kn given theta. It once again comes out as a product y equals 1 to n. For all values of theta, the function f tilde evaluated for the sample is equal to the likelihood. So basically, L tilde of theta is L tilde of theta for x1, x2, all the way up to xn. And this is equal to f tilde x1, x2, xn given theta for a product from I equals 1 to n or f of xi given theta. So this ultimately is nothing but a product over n likelihood functions. A similar relation holds for the discrete variates. When we have a sample of independent observations, usually it's convenient to consider the logarithm of the likelihood. And this is called the log likelihood. It's easy to see since the overall likelihood is a product of individual likelihood functions. The log likelihood becomes a sum of these individual log likelihoods. So far we have considered the likelihood of samples of independent, identically distributed variates. Also, the case where two independent experiments measure the same quantity x is of considerable interest. The combined likelihood is just the product of the individual likelihoods. So let's say we have experiments A and B, and these measure the quantity x. In this case, f of x1, x2 given theta is nothing but a product of phi of x1 given theta, f b of x2 given theta. Now, L theta is nothing but f x1, x2 theta. This implies L equals LA times LB, and log of L is basically just a sum So the likelihood of several independent observations or experiments is equal to the product of the individual likelihoods. Correspondingly, the log likelihoods add up. But to discriminate between hypotheses, what we use is the likelihood ratio. Now, of course, when we have to choose between more than two hypotheses, there are several independent ratios. So as an example, let's consider the likelihood ratio for two decay time distributions. So here's a sample of n decay times, which will denote by Ti, has been recorded in the time interval T that lies between some T minimum and some T maximum. The times are expected to follow. So let's say hypothesis 1 says that the times should follow an exponential distribution. Hypothesis 2 suggests that they should follow a uniform distribution. I want to know how likely are the first or the second hypothesis. So first we'll normalize the PDFs, which basically gives us when T becomes 1 by tau or minus T by tau. F2T, since it's just a uniform distribution, is nothing but 1 by T max minus T min. The likelihoods are equal to the product of the PDFs at the observations. So similarly L2, so L2 is simpler. Now defining or identifying T bar as the mean value of the times gives us the likelihood ratio. Now based on this, we can, for different values of the various quantities, we can see what is more likely, L1 or L2 or hypothesis 1 or hypothesis 2. So next, let's move on to a very important topic known as the maximum likelihood method for parameter inference. So let's say we allow for an infinite number of hypotheses by varying the value of a parameter. As in the discrete case, in the absence of a given prior probability, the only available piece of information which allows us to judge different parameter values is the likelihood function. So, in that case, it makes sense, or it is plausible, to choose the parameter such that the likelihood is as large as possible. And this is basically the maximum likelihood estimate, or MLE for short. So here on now we'll basically assume that the likelihood function is continuous and differentiable and has exactly one maximum inside the value range of the parameter. So what is the recipe for single parameter? So let's say we have a sample of again n IID observations, independent and identically distributed. If we denote by x1 up to xn from some PDF with unknown parameter theta. And we can form its likelihood or the log likelihood in the following way. So to find the maximum of L, log L and L have their maximum at the same location, we derive the log likelihood with respect to the parameter and set the derivative equal to 0. The value theta hat that satisfies the equation obtained thus in this way is the maximum likelihood estimate of theta. So basically, this is the equation, and theta hat gives the MLE of theta. Since only the derivative of the likelihood function is of importance, Factors in the likelihood or summands in the log likelihood, which are independent of theta, can be omitted. The estimate theta hat is a function of the sample values. And because of this, it is a statistic. Now this point estimate has to be accompanied by an error interval. The point estimate and error interval form an ensemble and cannot be discussed separately. Choosing as point estimate the value that maximizes the likelihood function, it is natural to include inside error limits parameter values with higher likelihood than all parameters that are excluded. This prescription leads to the so-called likelihood ratio error intervals. We'll discuss error interval estimation in a separate video, but it's important to remember that just the point estimate is not sufficient. Okay, as an example, let's look at the maximum likelihood estimate of the mean life of an unstable particle. So once again, given n decay times, Ti of an unstable particle with unknown mean life, for an exponential decay time distribution, f of t given gamma, gamma e to the power minus gamma t, with gamma equals 1 by tau, the likelihood is basically given by product over n such distributions. So it's gamma to the power n is a product over the exponentials minus gamma times Ti. Since an exponential is involved, a product over exponentials becomes the exponential of the sum. So this is summation from I equals 1 to n of gamma times Ti. The log likelihood just n times log of gamma minus gamma times the estimate, which will denote by gamma hat. It satisfies so the estimate is just equal to the mean value t bar of the observed decay times. Now, in practice, the full range up to infinitely large decay times is not always observable. So let's say if the measurement is restricted to an interval, let's say t between some 0 to t max, 0 to some t max, the probability distribution function changes and it has to be normalized, renormalized. So f of t given gamma in such a case, the log likelihood is n times the log of gamma is the log of 1 minus exponential of minus gamma times t max. We'll subtract this from this. Gamma times sum from I equals 1 to n of ti. The maximum is now located at the estimate that fulfills a relation like this. Now we see that this result reduces to what we had earlier if Tmax could go all the way to infinity. But here we have sort of a transcendental equation and this has to be evaluated numerically. Now this is where we'll stop this introductory discussion on parametric inference, likelihood functions, and maximum likelihood estimation. And we'll continue to take a more in-depth look into maximum likelihood estimation in the next lecture.